The roots are complex, and this is why. Let's call the roots in that case, we know that the roots are of the form a plus or minus bi. There are two roots, and they're complex conjugate. All right, let's take one of them. What does it correspond to in terms of the exponential? Well, remember, the function of the r was, it's this r when we tried our exponential solution. So what we formally, this means we get a complex solution. The complex solution, y equals e to this, let's use one of them, let's say a plus bi times t. The question is, what do we do with that? We're not really interested. I don't know what a complex solution to that thing means. It doesn't have any meaning. What I want to know is how y behaves or how x behaves in that picture. And that better be a real function, because otherwise I don't know what to do with it. So we're looking for two real functions, the y1 and the y2, but in fact what we've got is one complex function. All right, now a theorem to the rescue. This I'm not going to save for Wednesday because it's so simple. So the theorem is that if you have a complex solution, u plus iv, so each of these is a function of time, u plus iv is a complex solution to a real differential equation with constant coefficients. Well, it doesn't have to have constant. It has to be linear. Let me just write it out. To y double prime plus a y prime plus by equals 0. Suppose you got a complex solution to that equation. These are understood to be real numbers. They're the constants, the damping constant and the spring constant. Then the conclusion is that u and v are real solutions. In other words, having found a complex solution, all you have to do is take its real and imaginary parts, and voila, you got your two solutions you were looking for the original equation. Now, that might seem like magic, but in fact, it's easy. It's so easy. It's the sort of theorem I can spend 1 minute proving for you now. What's the reason for it? Well, the main thing I want you to get out of this argument is to see that it absolutely depends upon these coefficients being real. You have to have a real differential equation for this to be true. Otherwise, it's certainly not. So the proof is, what does it mean to be a solution? It means when you plug in a u plus iv plus prime plus b times u plus iv, what am I supposed to get? 0. Well, now, separate these into the real and imaginary parts. What does it say? It says u double prime plus au prime plus bu. That's the real part of this expression when I expand it out. And I've got an imaginary part, too, which all has the coefficient I. So from here I get v double prime plus I times av prime plus I times bv. So this is the imaginary part. Now, here I have something whose the real part plus the imaginary part, I times the imaginary part, is 0. Well, the only way that can happen is if the real part is 0 and the imaginary part is separately 0. So the conclusion is that therefore this part must be 0 and therefore this part must be 0, because the two of them together make the complex number 0 plus 0i. Now, what does it mean for the real part to be 0? It means that u is a solution. This, the imaginary part, 0, means v is a solution, and therefore, just what I said, u and v are solutions to the real equation. Where did I use the fact that a and b were real numbers and not complex numbers? In knowing that this is the real part, I had to know that a was a real number. If a were something like 1 plus I, I'd be screwed. I mean, because you know, then I couldn't say this was the real part anymore. So saying that's the real part and this is the imaginary part, I was using the fact that these two numbers, constants, were real constants. Very important. Well, so then how do I solve my, so what is the case 2 solution? Well, what are the real and imaginary parts of a plus bit? Well, y equals e to the a plus at plus ibt. Okay, you've had experience, you know how to do this now. That's e to the at times, well, the real part is, let's write it this way. The real part is e to the at times cosine bt. Notice how the a and b enter into the expression. That's the real part. And the imaginary part is e to the at times the sine of bt. And therefore the solution, both of these must therefore be solutions to the equation, and therefore the general solution to the ODE is y equals, now you've got to put in the arbitrary constants. It's a nice thing to do to factor out the e to the at. It makes it look a little better. And so the constants are c1 cosine bt and c2 sine bt.